Have you ever wondered why your camera flash charges up before it fires? Or how your computer keeps running for a moment even after power is cut? The secret lies in one humble but powerful component: the capacitor. In today's video, we'll explore what a capacitor is, how it works inside a circuit, and why engineers rely on it in everything from smartphones to power grids. First, types of capacitors. There are several types of capacitors, each suited for specific applications. Ceramic capacitors are small, non-polarized, and widely used in general electronics. Electrolytic capacitors have high capacitance values and are polarized, often used in power supply filtering. Tantalum capacitors are similar to electrolytic, but more stable and compact. Film capacitors offer high reliability and are used in precision and high-frequency circuits. Supercapacitors, or ultracapacitors, provide extremely high capacitance and are used for energy storage. Mica and paper capacitors are less common today, but were used in older equipment for stability and insulation. At its core, a capacitor is like a tiny rechargeable container for electric energy. But unlike a battery, which stores energy chemically, a capacitor stores it electrostatically. Picture two parallel metal plates placed very close together, with an insulating material, called a dielectric, between them. When you connect the capacitor to a battery, electrons rush onto one plate, giving it a negative charge, while the other plate loses electrons and becomes positively charged. The electric field that builds up between the plates is what actually stores the energy. Now here's where it gets interesting. Capacitors don't let current pass through continuously, since the dielectric blocks electron flow. Instead, they charge up and then discharge later when the circuit needs energy. This ability to absorb and release charge almost instantly makes them incredibly useful in electronics. Let's talk about charging in more detail. When a capacitor is first connected to a battery, current flows as electrons pile onto one plate. At the start, the charging is fast, but as the plates fill up with opposite charges, the electric field pushes back harder and harder. Eventually, the capacitor reaches the same voltage as the battery, and charging stops. Disconnect the battery, and the capacitor holds that stored energy like an electrical spring. The moment you connect it to a load, say a light bulb, the charges rush out, discharging the capacitor until it's empty. In circuits, this charging and discharging behavior becomes very powerful. For example, in a camera flash circuit, the capacitor slowly charges up from the battery, then releases all its stored energy in an instant, producing that brilliant flash of light. In power supplies, capacitors smooth out ripples in voltage, acting almost like shock absorbers for electricity. In audio systems, they filter signals, separating low and high frequencies to deliver crisp sound. Even in digital electronics, capacitors act as tiny reservoirs, ensuring stable operation for processors that switch millions of times per second. Different types of capacitors exist for different jobs. Ceramic capacitors are small and used for filtering high-frequency noise. Electrolytic capacitors, larger in size, can store much more energy and are common in power supplies. Supercapacitors, on the other hand, are designed to hold enormous amounts of charge compared to normal capacitors, and are even being explored for powering electric vehicles. One fascinating aspect of capacitors is how they combine with resistors to create timing circuits. Ever heard of the term RC time constant? This refers to how long it takes a capacitor to charge or discharge through a resistor. It's the principle behind blinking lights, delay circuits, and even early forms of memory storage in computers. If you found this explanation helpful, don't forget to like, share, and subscribe to Electroscope. And let me know in the comments which use of capacitors surprised you the most.